Good. So the last day we dealt with basic integration, right? We talked about integrating some very elementary functions, polynomials, um, the exponential function, and so on, right? Um, Today we want to look at integrating products. And there are a number of techniques. The intention in this lecture again, and the entire course, was not meant to exhaust all the possible functions that are out there and how to integrate them. As I told you, this is just an introductory course, and you are just being introduced to some basic techniques that are used to integrate products. Right? Keep that in mind as we go along. So this is the first type you can have, right? Notice here, and you're going to make use of what we refer to as the recognition aspect of integration. If you were to if you were to look here in this box, you realize that they're saying here that if you recognize that a function is such that the derivative of the inner function is out here. In other words, the function really is a product of some function times its derivative. Well, the integral of it will simply be e to the u. Right? And that came from, remember when we were differentiating, look here. If you differentiate e to the u, what would that be? Well, you'll have e to the u times du dx. In a similar way, if you recognize that, well, okay, the function you are integrating is really the product of the derivative of this inner function, well, then your integral is simply e to the u. Right? And we got some examples here. Look here. You can see that 2x is the derivative of this x squared here. Therefore, our integral is e to the x squared. And of course, you don't know if there was a constant. So we have our k at the end here. Look at another example. Look here. This cos x in front here is the derivative of this sine x. So right away you can see, oh, the integral is e to the sine x. Because if you take this and you differentiate it, you get that. And that's a way to check, just like when you were doing equation, you got an answer, x equal 1. The one who is that the right answer, you check. You put it back in the original equation and see if it works. Well, in the case of differentiation and integration, when you integrate a function and you want to know, well, am I right? Well, you simply differentiate back your answer and you should get what you integrated. Right? So that's a way of checking. It's a little more work. And sometimes laziness comes in the picture and you say, man, you will check none. But then sometimes you miss out, right? You can very well have the wrong answer. But because you don't take the time to check, well, things happen. Good. Not every time the integral, is really the exact. Like, okay, let me highlight this one here. This third one here. So sometimes what is in front is not exactly this x squared here, for example, is not the exact derivative of the x cube on top here. And therefore you might want to say, man, this method can't work. Not really. Maybe it can still work. Because think about it. You can rewrite this x squared. Right? You can rewrite this x squared as the derivative of this x cube and just stick in a fraction in front here to balance things out, right? So instead of writing x squared, write 3x squared, which is the And this time 3x squared is the exact derivative of x cubed on top there. But remember, that's not your function that you are integrating, right? You want x squared alone. So you stick a 1/3 there to balance things off. So 1/3 by this 3 will give you back the 1 that is in front here. You see? So that's a smart technique. And as I told you, if you know how many techniques there are, right, to integrate functions, as I told you, you can study for years and you're not going to get all of them, right? And there are many unsolved problems when it comes to integrating functions, lots of them, right? Yeah. So to get the x squared that we want, we stick this 1/3 here. So this 1/3 and this 3 is going to cancel. So in effect, this expression is really equivalent to this one. But now we have a situation where this 3x squared is the exact derivative of this x cubed. Therefore, we can now integrate this whole part here. We can integrate this whole part here and get that, right? This piece here. And this 1/3 comes back here. See? And you can quickly, by sight, you can differentiate back that, right? And you differentiate 1/3 e to the x cubed, you will see that you do have x squared e to the x cubed. Right? You can do that and see that it's true. You think you're following that? So look for those patterns, you know, where the function really is a product of a certain function and the derivative of the inner function, right? Like you see here. It's as though there's a this here is the derivative of that, right? Look at this one. This here is really the derivative of this inner function here, right? I know in this case you always have these function involving e and so, but there are exceptions, and so you might see later on. Good. Now you would want to say, man, sir, but if I can't recognize the thing, so what are you gonna do? Because you know sometimes you stare at something wholly and you ain't seeing it. Maybe I'm doing all this talking and we're pointing to these examples and you ain't seeing it. Now the question is, do we have a more systematic approach? That if you can't see, you know, that inner function being the you know, the derivative is in front and so on. It's all right. There is a systematic approach to come up with the integral, right? And we'll turn to that next. And we are going to do what we call, well, some books call it a U substitution. And well, this textbook that I took this example from calls it change of variable, right? So you hear about the U substitution, you hear change of variable, right? So let's take some examples to illustrate this change of variable method or the U substitution, right? And again, this is only one way. When you, maybe if you watch some YouTube videos, if you read another textbook, you're going to see a number of different approaches that might be slightly different, and maybe you like those better than the approach of this textbook. And nothing is wrong with that, right? You can go ahead and use it. Good. So here you can see that, well, the inner function here, x cubed plus 5, the derivative of that is some like let me call it a multiple of x squared, right? Because you'll get 3x squared, but this is just x squared. And whenever you see that happening, where what happened there? Whenever you see, one second. Whenever you see my pen start misbehaving now. Okay. Whenever you see this function in front here, this part here of the function is some multiple or some fraction of the derivative of the inner function, well, then this method might very well be suitable, right? So you got to look for that. Look for that. Because as I told you, we're going to look at several different ways of integrating functions now, right? And you want to know, well, how do I know, sir? How do I know which method to use? Just now you talk about recognition, now you talk about change of variable. How would I know? Well, I'm telling you, really recognition will work here, right? Recognition will work, but you got to be really, really good, you know? But now, if you watch this function, this is really this. X squared bracket x cubed plus 5 to the half power, right? So watch here. This, you see here, in this inner, let's take this as the function on the inside, right? X cubed plus 5, once the derivative of that part, right, is some multiple or some fraction of this, use substitution or changing the variable is the way to go, right? And you can see that the derivative of x cubed is 3x squared. So that's a multiple of x squared in front, right? So you say, oh yes, change of variable is what we'll go with here. Now, what do we mean with our change of variable? When we talk about change of variable, really, what we're saying is that, look, integrating this thing with respect to x is too hard. So what we'll do a substitution. And we'll change up, or we will write this function in terms of another variable, in this case, u. And that function is supposed to be simpler. That's your goal. You want to do it so that you end up with a function that involves u, but it is much simpler to integrate, right? So that's what we're doing here. So what you normally do, and this is, you can, you know, blindly do it. You take the inner function, you take this inner function here, you let that be u, right? X cubed plus 5, you let that be u. From that, and then you can see it here. From that, from this, what do you see? You see that du dx is equals to 3x squared. Now, if I take this dx over there, you know, you end up with du is equivalent to 3x squared dx. Now, these are not, remember, these are just what you call operators, right? But if you watch the videos on Leibniz notation, so you can operate as though they are like fractions, right? So the very operations you perform in fractions, you can perform here, even though the du and the dx are really operators. So what this statement here is saying, what this line is saying here, is that if you have something in front here with respect to u, you know, if you're integrating something with respect to u, it's equivalent to integrating something with respect to, let me put it, 3x squared dx, right? Or to put it more correctly, you're integrating something times 3x squared with respect to x, right? Good. So what is the use of all of this? What's the use of all of that? Well, if you look carefully, our original function up here, our original function, if I am to write it back as the integral of that, right? So, okay, well, they have it here, right? They have it here, they have it here. I just removed the radical sign here, right? We can write that back now in terms of u. Now, our original function, look at here. Isn't it the same as this? Look at it. The x cubed plus 5 to the half, that's this piece, right? The dx is this dx. Now, notice the x squared matches the x squared, right? This 3 and this 1/3 will cancel out, right? So we actually rewrite our original integral in terms of this 3x squared dx. And you might say, well, sir, how do I know how to do that? All that is required usually is some fraction in front here or some multiple in front here that will cancel this number in front here. Right? That's often what is required. Because remember, in the original thing, you got x squared here. But here we have 3x squared. But you don't want 3. That if the original function didn't have a 3 there, all we got to do to make it the same, multiply by a 1/3 in front. Right? So that neat trick will get rid of the 3. So we still have our original function. It takes some practice, it takes some concentration, it takes some doing to master this, you know. So you're writing your function now because you want to write it with this 3x squared here. You want to write it with that. And I'll show you why just now. I'll show you why. Right? Y'all are following me so far? Give me some feedback, you know. Hello?
Yes, sir. Following.
Yeah. Now, why did we do that?
Yes.
In one of the videos, I did mention that sometimes you make things more complicated, but for a purpose. Right? There's a purpose behind the whole thing. Right? So this is here. Watch this thing. This thing is far more complicated than we started with. Why are we doing all of this? Well, we want to, as the topic says here, we want to change the variable, right? So look what now. Remember we said that all of this is equivalent to du. So we replace that with du. See? All of this is u. So this whole long expression now, written in terms of u is this. And now, if you have to integrate u to the half, that's very simple because we learned that last week or the other week when we did basic integration, right? So you know you do your thing to add 1 to the power there, it becomes 3/2, and then you divide by, well, dividing by 3/2 is the same as multiplying by 2/3, right? And now you have a very simple, well, you end up with, look, notice here, all of this will become 2/9. We write back this now in terms of x. So 2/9, that's this here. U to the 3/2 is this, right? Plus your k. You see? So you change up this very complex function that was written in terms of x to something much simpler and easier to integrate in terms of u. And then when you finish integrating, well, you revert back to x. Right? The hardest part of this whole process is when you have gotten this equivalence here. You have to be able to write back your original function and involve this equivalence. Oftentimes, right? More often than not, what you have to be doing is find some fraction in front of you. Most of it is a fraction you're looking for. Right? If not a fraction, some multiple, maybe a 2 or 3 or a 4, you know? So often it's just a matter of sticking a 1/3, a half, a quarter, 1/5, you know, or a 2, 3, 4, that sort of thing. So let's take another one. This is another example. So here we want to integrate cos x sine x cubed, right? Cos x sine x cubed. Now, what you're seeing here, of course, we can write that back. We can write this as like this here, right? Inner function being sine x. And you can see, as I told you, it kind of satisfies the little condition that I mentioned before. This is the derivative of this inner function here, right? So this is one that doesn't involve E. So cos x is the derivative of sin x. I say, oh yes, this change of variable thing can work here. So we let u, notice here, we let u be the inner function sin x. We differentiate and then cross multiply. So in other words, you did this. You take this, for that missing step. This textbook, they assume things quickly. Du dx equal to cos x, right? And then they take over the dx. So you get du equal to cos x dx, right? And that's what they have here. So you can stick something in front here and you can stick something in front here to integrate, right? You can and then integrate here. That's what's happening here. So this is our original function. We want to write it with this cos x dx. So well, cos x dx, that's this here. Sin x cubed, that's this here, right? No problem there. And in this case, look at what happens. This thing is the direct equivalent of du. This is u cubed. So you didn't have to put no fraction and so in this case. You can actually do it by recognition, right? Well, I'm just showing you that let's say you can't recognize the thing. Well, substitution can work. So now we can write back this here as, remember this whole thing is du. This is u cubed. And you integrate. When you integrate that, you get this. So the integral of this is that. Could you follow this one?
Yes, sir. The last line there.
Here, this line?
Yeah.
What about it? We simply write back this u. Well, it's really sin x, right? U is sin x.
Yeah. Yeah.
Yeah. Well, the 4 on the here is like a quarter, right? You just, yeah. You get it?
Oh, yeah. Seen it.
Yeah. Right. And some of these things I told you, you can watch me do. Well, I can't do so many examples. I can do 1 or 2, but you got to do a lot of them. As you do it, it becomes second nature to you. And there, as I told you, there are lots of variations in the technique, right? That sometimes, you know, you can't expect people to cover all the things in examples. As you do, then you say, oh, I need to tweak this, I need to tweak that, right? I've seen cases where instead of, like I mentioned earlier, where you might have to stick a fraction like half, 1/3, a quarter. You say, and you think that, but then one of them, you have to stick a fraction like 2/3. And you say, wait, sir didn't tell me that. Well, if I have to do all the examples in the world, well, you can imagine, right? Good. This is another method we're turning to now. Integration by parts, right? And some of them, some of the products that you will meet up, you'll have situations where the function that you have to integrate is very complicated. But you can make use, if you notice this here, this really comes from the product rule, right? I don't know if you recognize it. Do you see that if I take this over there, what you get? Remember that thing, but u dv dx plus v du dx. Remember that thing?
Yes, sir.
Yeah. I'm not going to, in this part of the lecture, explain, well, you know, how they really come up with this, right? I'll just give it to you. Maybe you can on your own look up its derivation and so on, right? But making use of this result, you can integrate certain products. And what you were looking for really, you want, if you notice, the integral of this ends up, you have to do another integral over here, right? But if you do integration, you got to do some integration somewhere. But you want this integral to be easier than this one here, right? You want this one to be simpler than that one. Good. To illustrate, let's use this example. You have to integrate x e to the x, right? So that's this one here. So we don't have a method to really integrate that directly. So what we're going to do, we're going to make a substitution. We're going to make, let's say, okay, in this case, let's say we make xv, and we're going to let du dx be e to the x. Now, before I go any further, right, do not assume that because the function is written like this, then x automatically becomes v, and e to the x becomes du dx. No, it doesn't mean that. There are times when the term that, let me say the term or the factor that is behind might very well be what you should make v, and the factor in front should be du dx. And you know what will tell you that? When you do this procedure I'm going to show you now, you end up with something at the end here that is harder to integrate. When that happens, the procedure is telling you, you know what? You didn't do the right substitution at the beginning, right? Good. So let's follow the procedure. So we let v be x, and you let du dx be e to the x, right? So that's what's happening here, there and there. From this, we can get dv dx, which is 1, right? Because v is x, then dv dx is 1. And if du dx is e to the x, well, the integral of that, you integrate this to get u, right? Well, this is easy. We all know that. When we integrate e to the x, we end up with e to the x, right? Good. Now you want to say, well, what happened to the k and so? Well, remember there is an integral in the formula. So when we finish it all, we're going to put 1k at the end. Good. So we're going to put everything in the formula, right? We're going to put everything in the formula. So we got this. So we know u and we know v, right? This is u, that's v. So we put it there. Minus the integral of u, we know u again, right? U is e to the x, and dv dx is 1. So look at what you end up having to integrate. You have to integrate e to the x only. You see that? You end up having to integrate e to the x, which is, of course, you know, e to the x. And that's your answer. So what you end up at the end here with is simpler to integrate than what you have to integrate. See? And that's why this method works. Now, in your own time, right, I'm not going to indulge you here. In your own time, you make the wrong stuff. You go home, or you're at home when you finish this class, do the wrong substitution. Let this x here, let that be du dx, and let e to the x be v, and see what happens when you come to this substitution here. Right? I'll give you a hint. This is going to be more complicated to integrate than this. And then you realize, nah, boy, I got to do the wrong substitution. Right? And you realize, no, I need to go back to the beginning and switch the substitution around. Right? Try it on your own sweet time afterwards. Let's look at an example. So you want to integrate x to the 4 ln x, right? So I guess we need to write the formula, you know? We write the formula. Integral of, what was it, v du dx is equals to uv minus u dv dx, right? Good. Now what's something? Look something. This is a good example to bring out. You notice here that they didn't say that, okay, this is V and this is du dx. No, right? If you do that again, you will see what I'm telling you, end up with a very, very complicated thing. In this case, I mean, the author don't try it and see that if you make x to the 4, if you make x to the 4 V and you make ln x du dx, it will lead to something more complicated. So in this case, you have to make ln x V and x to the 4 du dx. See that? This is just what I was telling you just now, that don't assume that because x to the 4 is in front, oh, that's phi, right? So don't think that there is like a, this matches that and that matches that. No, don't do that. And again, how would you know that? You say, sir, how are we going to know that? Me just learning this thing. Well, you're learning the hard way in that when you do that, when you make that match and you work down the problem and you reach down here, you end up with something so complicated, you want to tear up the book, right? But then don't tear up the book. Just go back now and switch your substitution around. And I guess that's what this author did, right? Unless they copied it from somebody, of course. So they made the substitution, V is this. So dv dx is this. Then du dx is this, and then u is that. Good. So we're making the substitution because we got u, we got v, we got du dx, we got dv dx. We put all in this formula, right? The same formula here. Look, it's here. And when you work all this complication, look how it ends up nice, right? Of course, I bring the 1/5 to the front. And this is easy to integrate. Because when you integrate that, you get that, right? When you multiply by the 1/5. So this very complicated thing, look how it's easy to integrate. Follow that one?
Yes, sir.
Good. So this technique was very valuable because for a long time, they were not, or mathematicians had some difficulty integrating ln x of itself. We know how to differentiate ln x, but how do we know to integrate ln x? Right? And some smart Alex, I wish I knew the history, thought of ln x and said, look, why don't we treat ln x as 1 times ln x? And that makes it a product. And we can now use this very method and integrate it. And that's what they did, look. They let V, notice again in this case, V is not the 1 in front. V, they use as the factor the back, right? So they treat ln x as 1 times ln x. You let that be V, so dv dx is 1 over x. And you let du dx be 1, which makes u x, right? You integrate 1, you get x. And you put all of this in this formula, right? And look at what happens. We get x ln x minus the integral of x times 1 over x. This cancels out, right? You can see that. And you get 1. So when you integrate 1, you get x. So your answer is x ln x minus x plus p. Very, very smart. Follow that? No response.
Yes, sir.
Good. So let's turn our attention now away from products. And let's talk about fractions now, or quotients, right? Rational functions. And how do we integrate those? Let's see some methods again. Again, this is not to exhaust all the methods out there and all the functions that you need out there, right? I'm happy I heard Dominic's voice just now because they're going to do a course called Calculus 2. And that is more, that course should be renamed Integral Calculus, right? or integration or something like that, because that entire course is about integration and its application, right? You hardly do any differentiation there. Maybe a recap, and then they'll bring in the hyperbolic and so, right? And then we switch straight over to some heavy integration. A lot of substitution, trigonometric substitution, T substitution. Oh my, you name it, it's there.
Sounds like an interesting course, sir.
Yes, differential equations and so, yeah. So let's talk about this here. So again, the recognition factor comes in here, right? If you see a fraction where the numerator is the derivative of the denominator, right away, you know that that function is ln of, well, the function that was under there, right? And you know where you got that, because when you differentiated ln of u, what did you get? You get 1 over u times the derivative of u. Is that what you did, right? So that is where that came from. Integral of a function where the numerator is the derivative of the denominator, right away, that's your answer. Again, what might happen here is that the numerator might not be the exact derivative of the bottom. You might have a multiple or a fraction of the derivative of the denominator. And then by just sticking a fraction in front, you can, be able to integrate a number of them. Right? So keep this in mind as soon as you see this. If the numerator is the exact derivative of the denominator, this is your answer. Right? And notice they have a bar around here because the function, whatever it evaluates, there must be positive, because you can't have the ln of a negative number, right? Because of the nature of the ln function and so on. Right? And we dealt with that in videos before. Good. So let's take one. Maybe they'll give us an example where this is not exactly the derivative of the bottom. Right? So let's see this one. This first one, look here. Exact. Cos x is exactly the derivative of the denominator, right? Sin x. When you differentiate, you get cos x. Exact. So nothing you have to do there. Lazy man, right? Well, here, look at this one. The integral of x squared over 1 plus x cubed. Now, x squared is not the exact derivative of this, right? However, if you see that, okay, well, look, you want the exact derivative of up here, 3x squared. But this 3x squared is not exactly like this. Now, how do you make it like that? Simply stick a 1/3 in front. See that? So this 1/3 is going to cancel out that 3, and you actually get what you want to integrate, right? So these are equivalent expressions. This is equivalent to that. And then now you have your situation where the numerator is the exact derivative of the denominator. You put that there, stick the 1/3 in front, stick in your key, right? In the third one here, this one here, exact. You have to do no work at all, right? You're getting that so far?
Yes, sir.
Good. Now look at changing the variable now for fractions or quotients or rational functions. So here, again, the same thing holds. If you see the bottom here, right? When you watch the inner function here, the bottom, when you differentiate that, you get what is on top there. Or even if you don't get exacting, you get a multiple or a fraction of that. Well, then you know what? Change of variable might very well be what you need, right? Good. So you look here, you say, look, let's say we do the u substitution, but this is rather complicated, right? This is rather complicated. So if we were to let u be x squared plus 1, and then we do the manipulation here. I'm going to write back this thing now in terms of this 2x dx, right? So look here. This writer, they're lazy, right? And she jumped the gun. It's two ladies write this book, you know. The women getting lazy these days. Yeah, good. Let me write that back, right? So this here, I'm going to take this and I'm going to write it on, let me come back to this just now. Yeah. So this here, you notice it's 2x dx 1 over the root of x squared plus 1, right? Y'all see that?
Yes, sir.
Yes, sir.
This is what we have to differentiate. Sorry, integrate. So I'm taking this 2x at the corner there, you know? It's the same thing. It's as though I just moved the 2x there. So this is our du. This is really 1 over u to the half, right? Right? So this whole expression here really becomes this. Becomes that. And then that, well, we can write it like that. And that's easy to integrate, all right? It's this. And then you write it back in terms of x. Right? I guess the writer jumped a little step there. You follow it?
Yes, sir.
Yes, sir.
Good. So that's change of variable here, right? That's change of variable. Applied now, not to products, but to quotients, right? This is another example. Look at this one. So in this case, cos x is the derivative of the inner function of the denominator, right? Sin x. Good. You do the substitution, right? And you change the variable. So notice, again, cos x, what? Cos x dx is really du, right? Isn't that so? So we're replacing all of this with du. And the 1 over sine x to the 4th power is really 1 over u to the 4. And this here now you can write as u to the minus 4, right? And you integrate that, you add 1, and you do your thing, and you get this. And then you write it back in terms of sine x. Because u is really sine x. Notice in this case, they put a k in front, just, you know, rather than this thing sticking out here. They take the k and put it in front. Follow that?
Yes, sir.
Yes, sir.
And then there's a last method. Now, when I say last method we will consider, right? I told you already, we're only scratching the surface here, right? The teachers who are going to go on to calculus 2 would see me next year and laugh at me and say, that's Japanese, you know, you show us last year, right? You're teaching them small children thing to us, you know, right? They'll tell you next year what calculus really is. Yeah, and this is a third type. So let's say you have and here it's a rational function, right? It's a rational function. It's a little different from the ones you saw before. So here, remember we did this thing called partial fraction? Y'all remember that when we were doing differentiation? Are you familiar?
Yes,
sir.
sir.
Yeah. So you take this and notice that the writer did not waste time showing you all the steps. You take this fraction and you split it up into two parts here, what we call the partial fraction of the bigger fraction, right? You break it up into two using that long method that we did already. So we skip out all of that. Now that we have this, then to integrate this is the same as integrating these two, right? Which you see here. And integrating these two, well, shouldn't be hard because the integral of 1 over a linear function is this here, right? And the integral of this is this. And then you can use your laws of logarithm to combine them, and you get that. Right? Follow it? So I know you say, wait, man, how you get this from this to this sort? Well, we did partial fractions. I even included one in the test. I think students did pretty well. Maybe you get a friend who work it out and just send them the answer. I don't know. Let me see how long that will go on for. All right, so learn your partial fraction. You take your, I wouldn't go further when, you know, this is more complicated, like you have, I'll try to avoid, you know, where you have a third one, maybe that would be too hard, or you have a quadratic fraction, quadratic factor in the denominator, or a repeated factor. I wouldn't, you know, go that far. I'll just go two nice linear ones, and that's it. As I told you, this is just an introductory course. Right? I don't want to kill you. Not kill you, fail you. Good. So you take this one, you split it up into two parts, and then you use your, what we did last couple of weeks ago. Right? We make use of that simple formula to integrate these two, which you get this and this. Well, this is algebra now. You combine them into one. Right? Good. So